Hello. In the previous lecture, we defined what a unique factorization domain is. Essentially, an integral domain is called a unique factorization domain if every non-zero, non-unit element can be written as a product of irreducible elements. And the way that we can write it should be almost unique. What does that mean? This means that these irreducible factors should be unique up to reordering and multiplying by units. So if we have such properties, we call such an integral domain a unique factorization domain, and we abbreviate it to UFD. And we also proved the existence part essentially by dividing and dividing and dividing again and again, and then we produced a chain of ideals, ascending ideals. And then we said a ring is Noetherian if every ascending chain of ideals terminates. We call that a Noetherian ring. And we show that a ring is Noetherian precisely when all of its ideals are finitely generated. So altogether, for instance, as an example of this result, that every Noetherian integral domain satisfies the existence part of this factorization, we deduce that PIDs satisfy the existence part of a unique factorization domain. Okay, so overall, again, let's repeat this. We showed that every Noetherian integral domain, for every Noetherian integral domain, the existence part hold. And we showed that every unital commutative ring is Noetherian if and only if, so a given unital commutative ring is Noetherian precisely when all of its ideals are finitely generated. So what we want to do today is to focus on the uniqueness part. So what does that mean? What does the statement mean? It means that when I write an element as product of irreducibles, possibly in two different ways, let's say I have a bunch of irreducible elements, P1 dot Pn, and another one's Q1 dot Qm, and I multiply the first bunch, and I end up getting the product of the second bunch. Then they should be essentially the same, meaning I should be able to, first of all, say they have the same number of factors. Second, I should be able to come up with some reordering of the terms. Let's say one goes to I1th term, and the nth term goes to I sub nth term. And so this is supposed to be a permutation of 1 to n. And for each one of these indices, I should be able to find a unit such that when I multiply the ith term or the I sub nth term by u sub, the I sub jth term by u sub j, I end up getting p sub j. So essentially, these irreducible elements are the same from multiplicative point of view. Their slight difference is that they might differ by a unit. So in the ring of integers, we also have this kind of property, and we have to be careful about this reordering and multiplying by units. For instance, 2 times 3 is the same as -3 times -2. So as you can see here, both reordering of the terms and multiplying by a unit, both of them are actually important, and we cannot ignore them. Okay, now in order to understand and capture the essence of uniqueness, we need to define what is a prime element. So this goes back essentially to Euclid's lemma for the ring of integers. So in the ring of integers, the way that we show a unique factorization, that one we call the fundamental theorem of arithmetic, the way that we show unique factorization of ring of integers is using Euclid's lemma, which says that a prime in integers divides a times b precisely when it divides one of them. So this is what we take as the definition of a prime element in an integral domain. So let's make it precise. So suppose D is an integral domain, and then because I want to work with P divides AB, I have to start on formalizing the concept of divisibility in an integral domain. So suppose D is an integral domain, then we say an element A divides an element B when, and write it like A divides B, like this, when B is a multiple of A in the ring capital D. So if I can find some element of the ring that I denote by small c, such that B is A times C, in that case we say A divides B. In the language of ring theory, we know that the principal ideal generated by A consists of multiples of A. So it's the same as saying, so this is equivalent to say that B belongs to the ideal generated by A. We'll come back to this comment later, and I record it as a lemma. But for now, let's go and define what is a prime element in an integral domain. So an element P, we call it to be prime if it satisfies the Euclid's lemma property. What do I mean by that? So first of all, we have to ignore the silly elements from multiplicative point of view. So meaning not zero and not unit. So this is kind of similar to part of definition of irreducible elements. So there again, we had to ignore zero and units. So here we do the same. So a prime element is never zero or a unit. Now, besides that, what is the meet property is that if P divides product of two elements, then it should divide one of them. So that's the main property of prime elements. But both of the properties are important, but this is often the property that distinguishes a prime element from the rest. Now, let's try to understand this divisibility a bit better. Again, as I've pointed out, A divides B precisely when B belongs to the ideal generated by A. And this is exactly the case when the ideal generated by B is a subset of the ideal generated by A. So it's kind of the reverse of inclusion. Divisibility is kind of the reverse of inclusion. But let's see what is the main result that we want. Okay, so what is the main result that's going to help us understand the uniqueness part of factorization domain? So suppose D is an integral domain, and suppose that I have already proved the existence part for this, meaning suppose that every non-zero, so suppose that every non-zero and non-unit element, so every non-zero, non-unit element of D can be written as a product of irreducibles. That's part of our assumption. I'm assuming that I have already proved the existence part. I know why the existence part holds. For instance, I can assume that D is a Noetherian integral domain, but it doesn't matter if it's Noetherian or not. Suppose that the existence part actually holds. Then this ring is a unique factorization domain precisely when, if and only if, every irreducible element is prime. So if I know that every irreducible element is prime, then I can deduce it's a unique factorization domain. So again, let me repeat. Let's assume that I do know the existence part of the factorization. That means I do know that every non-zero, non-unit element of this ring can be written as a product of irreducibles. From there, I want to deduce that D is a UFD precisely when every irreducible element of D is prime. Okay, so this is an if and only if a statement. So I have to be able to go from one side to another and vice versa. Let's go from left to right. So that means I'm assuming that my ring is a UFD. I want to show that every irreducible element is prime. Let me say that in this proof there are many small details, and I will present the gist of it, and you can see more details in the lecture notes. So there are very small details, many cases, but many of them are actually easy. I will just tell you the important part of the proof. So I want to say that every irreducible element is prime. What does that mean? I give you an irreducible element. It's automatically non-zero and not unit. That's part of the definition of being irreducible. So in order to show that it is prime, the main part is to show this property. So that means I need to show star. In order to show star, you have to show a star. Now, to show this, we start with the assumption that P does divide product of two elements, A and B. That means what? That means I can write down A times B as P times something, some element. Now what we'll do, we write down C, A, and B as product of irreducibles. Then we realize that AB is written as product of irreducibles where one of the factors is P. Now I use the unique factorization property of this integral domain, deduce that this irreducible factor P should appear among the irreducible factors of A or B. That means that P divides either A or B. So that's essentially the proof, but let's see a bit more details. So again, by the existence part, I can write C, A, and B as product of irreducibles. Suppose P sub i's are irreducible factors of C, Q sub i's are irreducible factors of A, and Q sub i's from Q sub 1 till Q sub n, and then from Q sub n plus 1 till Q sub n are irreducible factors of B. So again, these are irreducible factors of A, of C, sorry, irreducible factors of C. So then I have irreducible factors of A and irreducible factors of B. Now I plug them into the equation. I plug them into the equation PC equals to AB. Okay, so what do I get? I get that C is P1 dot PR, but you see, C might be a unit. So that's why I cannot, I mean, if C is a unit, there is no way of writing it as product of irreducibles. So that's why I also introduced this variable U, which is a unit, just in case if C was a unit, I just ignore the indices P1 dot PR and write it as C equals to U. The same goes for A or B. So I introduced these units, U, U prime, U double prime as auxiliary kind of variables, just in case if A, B, or C are units, then in that case, we do not have irreducible factors. This is one of those details that I have mentioned earlier. So the other detail is that we have to argue why we are done if one of these things is zero. So I leave it to you to think about it. So in any case, we write these guys as product of irreducibles, and then we notice that if one of them is a unit, then I can just ignore the irreducible factors. And now that I have these irreducible factors, we plug them into the equation P times C equals to A times B, and we get that U times P times product of irreducibles that are inside C, and then product of the irreducibles of B and C times the possible unit factors. These guys are equal. Now I use the uniqueness part. The uniqueness part says that these irreducible factors, including P, should appear among the irreducible factors that we have here up to a unit. So this means I should be able to find a unit and some index such that P is that unit times Q sub I. So it should appear it should be one of these irreducible factors. But that means that so it depends if what the index I is. It's either among the irreducible factors of A or among the irreducible factors of B, depending if the index is between 1 to m or more than m. So in the first case, then P divides the A. This is precisely A. This is how we defined A. And or if the index I is at least m plus 1, then it divides this product, and that is precisely B. So all together, we get that P dividing A times B implies that P either divides A or divides B. That means that P is a prime element. So we showed that unique factorization implies that irreducible elements, being an irreducible element implies that it is prime. Now we want to go the other way around. I'm going to assume that the existence part hold, and I want to show the uniqueness part. And the way that I want to show the uniqueness part is by assuming that every irreducible element is prime. So I start by two bunches of irreducible elements, assuming that the product of the first bunch is the same as the product of the second bunch. And I have to show that after reordering and multiplying them by units, I end up getting the same things. So what is the main tool? The main tool is that I'm going to look at each one of the irreducible factors of the left-hand side, find a match for it in the right-hand side, cancel them out, and at the end, because all the piece of i's will be canceled out, I get 1 on the left-hand side, and then that implies that there cannot be any irreducible factors on the other side. So this means that I've already exhausted the list of q sub i's. Okay, let's make it a slightly more formal. So p sub 1 divides this product on the left-hand side. Therefore, it divides the product on the right-hand side. So P sub 1 divides product of Q sub i's. But P sub 1 is irreducible. And by our assumption, every irreducible is supposed to be prime. So P sub 1 is prime. A prime element, when a prime element divides product of a bunch of elements, it should divide one of them. That's essentially the definition. We wrote it for two factors, but then you can deduce it for multi-factors. Because P sub 1 divides product of Q sub i's, Q sub 1, Q sub 2, Q sub n, it should divide one of them. So that means I can find some index, I sub 1, such that P sub 1 divides Q sub I sub 1. Okay, that means what? That means Q sub I sub 1 is P sub 1 times something inside the ring. It's a multiple of P sub 1. So I can find something inside the ring such that Q sub I sub 1 is P sub 1 times V sub 1. But remember, all Q sub j's are irreducible elements. So this is an irreducible element. This is irreducible. That means whenever I write it as product of two elements, one of them should be a unit. So either P sub 1 is supposed to be a unit or V sub 1. But P sub 1 is irreducible, so it cannot be a unit. Because P sub 1 is irreducible, it's not a unit. That means V sub 1 should be a unit. So we are in good shape because now we found a match for P sub 1 among Q sub j's. And when I say a match, I mean we found an index where P sub 1 differs by Q sub j only by unit multiplication. Now we plug in, instead of writing Q sub I sub 1, I write V sub 1 times P sub 1, and then I use cancellation law. Because I know P sub 1 is not 0, I can use the cancellation law. So I end up getting that P sub 2 times P sub 3 times P sub n is the same as, now I kind of don't have Q sub I sub 1 anymore. So all the other factors except Q sub I sub 1, so one of the factors on the other side is dropped, I've replaced it with some unit. V sub 1 is a unit, is not going to play an important role, as we will see. Now I repeat this process for P sub 2, P sub 3, and so on. So for each one of those, I will end up finding an irreducible factor theory in the other side. Let me emphasize one thing, that when I want to repeat this process for P sub 2, I have a possible unit factor in the other side. So possibly when I want to use this primeness of P sub 2, I have to say that P sub 2 divides this unit, but that's not possible. So think about this, that a prime, an irreducible element, or a prime, never divides a unit. Because if something divides a unit, it is a unit. So think about this. So let me write it here, that if A divides a unit, then A is a unit. Okay, so that means that P sub 2 cannot divide a unit. This means that I will be able to continue this argument and find a match for each one of the irreducible factors on the left-hand side in the right-hand side. So altogether, doing this process again and again, we end up finding indices I sub 1, I sub 2, I sub m among the numbers 1 to n. And I can find bunch of units, v sub 1, v sub m, such that q sub I sub j is p sub j times u sub j, v sub j, I meant to write. Yeah, so times v sub j. So essentially, we are repeating this argument that we had earlier for each one of these indices. So we plug in into the equation that we have, and then we cancel them out. We end up getting that 1 is on the left-hand side, and we get product of these units times the remaining q sub j factors. So the remaining q sub j factors. So this j is not among the indices that we have canceled out. Now again, because an irreducible element cannot divide 1, because 1 is a unit. So you see, on the left-hand side, we have 1. So this means all the factors on the right-hand side are units, because we can multiply them by something and end up getting 1. But an irreducible element is never a unit. So this means that this set of indices should be empty. None of these q sub j's should survive this process, as otherwise q sub j should be a unit. So again, that implies that this set is the entire set of indices 1 to n, but these I sub j's were distinct. We can deduce that m is n, and this is a permutation, and this completes the proof. We get the uniqueness part. Let's try again, understand the statement that we are proving. We've proved that if the existence part of being a unique factorization domain hold for an integral domain, then it is a UFD precisely when every irreducible element is a prime element. Okay, so now this tells us that we need to understand prime elements better. When we wanted to understand irreducible elements, we used the language of ideals, and that was extremely useful. We showed that an element is irreducible precisely when the principal ideal generated by that element is maximal among proper principal ideals. So this is what we showed for irreducible elements. And then from there, we deduced that if I am living in a PID where all the ideals are principal, this means that an element is irreducible precisely when it is maximal as an ideal, as a proper ideal. Okay, so what about a prime element? Can I understand it in terms of the principal ideal generated by that element? So let's, in order to do so, as I've mentioned it earlier, we need to understand the concept of divisibility in the language of ideals. Okay, so this I have already mentioned, but let's go over this, that A divides B precisely when B is an element of the principal ideal generated by A, and that happens precisely when the ideal generated by B is a subset of the ideal generated by A. Okay, so and let's see what happens if A divides B and B divides A. So A divides B and B divides A. This happens precisely when the ideal generated by A is the same as the ideal generated by B. At least when I'm working with an integral domain, I get this equivalence relation. This direction is always true, but the other way around, we need to assume that my ring is an integral domain. Okay, so let's go through the proof. It's actually one-line proof. I've already mentioned it. When I say A divides B, that means that B is a multiple of A, but the set of all the multiples of A form an ideal, and that is what we called the principal ideal generated by A. And when B belongs to this, and then all the multiples of B belongs to this ideal, and we get this, and vice versa. So immediately we get the first part. Now, if A divides B, then the ideal generated by B is a subset of the ideal generated by A. When B divides A, I get the other way around. So therefore, these ideals are equal. So that shows this direction of the second part. Now let's go that way. So when I tell you that two principal ideals are equal in an integral domain, so let me emphasize that D is an integral domain, then that implies that A and B differ by a unit multiple. So there exists a unit such that A is B times U, but when A is B times U, that means A is a multiple of B, so B divides A. But U is a unit, so I can multiply both sides by U inverse. I get that B is A times U inverse, and that means this time B is a multiple of A, which means A divides B. So we get this understanding of divisibility in the language of ideals. Now let's try to understand what is the implication about prime elements. So an element P is prime by definition when, first of all, the element is not zero, which is the same as saying that the principal ideal generated by P is not zero. Second, P is not a unit. Not being a unit is equivalent to saying that the ideal generated by P is a proper ideal, is not the entire ring. Okay, so now, so far we could translate all the conditions into the language of ideals. Now, how about the last one? P divides AB is equivalent to saying that AB belongs to the ideal generated by P. Now, this is supposed to imply that either P divides A or P divides B. But again, the way that we said it, P divides AB is the same as saying that AB belongs to this ideal. P divides A is equivalent to this, and P divides B is equivalent to this. So altogether, we get that being a prime can be translated into the language of the ideal generated by P. Okay, so this brings us to the definition of a prime ideal. We say an ideal I is a prime ideal if it satisfies the following properties. I is a proper ideal. So I is proper. Okay, maybe I use a different color. So I is a proper ideal. If A times B belongs to I, then either A is inside I or B is inside I. So this extra condition I don't impose. This condition of not being zero is not relevant for prime ideals. It is actually important to allow the zero ideal be a prime ideal as well. But besides that, we are still, we are essentially borrowing whatever we have seen over here and taking that as the definition of prime ideal. So an ideal is prime if, first of all, it is proper, and second, if A times B belongs to this ideal, then either A belongs to that ideal or B belongs to that ideal. That's the definition of being a prime ideal. So immediately we deduce that in an integral domain, an element is prime if and only if it is not zero and the ideal generated by P is prime. Okay, so we have an understanding of prime ideals now in terms of prime elements in terms of prime ideals. So we need to investigate prime ideals better. So in the case of irreducible elements, we had some kind of connection between irreducible elements and maximal ideals, at least in a PID. So then we were interested in understanding properties of maximal ideals. And the way to understand maximal ideals, we focused on the quotient ring, and we said an ideal is maximal precisely when the quotient ring is a field. So we showed an ideal is maximal precisely when the quotient ring is a field. Now, next we are going to try to understand a prime ideal in terms of its quotient ring. We show that an ideal is prime precisely when the quotient ring is an integral domain. It's quite interesting. So being a field implies that it's maximal. Now we are saying that it is prime precisely when the quotient ring is an integral domain. Okay, actually the proof is much easier than showing that an ideal is maximal precisely when the quotient ring is a field. So let's go through the proof. I assume that I is prime. I want to show that A over I is an integral domain. An integral domain is a non-trivial domain, which means the zero is not the same. Is a non-trivial ring, which means the zero is not the same as one. It has at least two elements with no zero divisors. Now, why is it not trivial? It's because a prime ideal is always proper. Because I is not the entire ring, the quotient ring consists of at least two elements. It cannot be just a zero ring. Now, why doesn't it have a zero divisor? So suppose that the product of two elements is zero inside this quotient ring. What does that mean? This is the coset. This is the coset represented by A times B. Now, two cosets are equal precisely when the difference of the coset representatives belong to the ideal. So AB plus I is a zero coset precisely when AB is inside the ideal. Now, I is a prime ideal. That means that when product of two elements is inside I, then either A is inside I or B is inside I, which means either the coset A plus I is zero or the coset B plus I is zero. And that's exactly what we wanted to show. So we show that if product of two elements in this quotient ring is zero, one of them should be zero. This means we do not have zero divisor inside the quotient ring. Now, let's go the other way around. Suppose that the quotient ring is an integral domain. I want to show that I is a prime ideal. So the first thing that I have to point out is that it's why I is a proper ideal. And that's immediate because A over I is an integral domain. As part of definition of being an integral domain, I can deduce that it is not the trivial ring. It has at least two elements, and therefore I is a proper ideal. So far, so good. Now let's focus on the more interesting part of being a prime ideal, meaning if the product of two elements belong to I need to show either A is inside I or B is inside I. Now, knowing that AB belongs to I deduce that the AB plus I is inside I, and therefore A plus I times B plus I is the same as the coset represented by zero, is the zero coset in the quotient ring. But the quotient ring is an integral domain. So when product of two elements is zero, one of them should be zero. So either A plus I is zero or B plus I is zero. So altogether, we deduce that either A is inside I or B is inside I, which means I is a prime ideal. Okay, so far so good. We showed that being a prime ideal is equivalent to saying that the quotient ring is an integral domain. From here, we immediately deduce that maximal ideals are always prime. Okay, so let's look at this. Let's see why this is the case. If I is a maximal ideal, we know that this means the quotient ring is a field. But every field is an integral domain. So from here, we deduce that I is a prime ideal, because the quotient ring is an integral domain precisely when the ideal is prime. So every maximal ideal is prime. Now from here, I can deduce that in a PID, irreducible elements are prime. So why is that the case? So suppose P is irreducible. That means the ideal generated by P is maximal among proper principal ideals. When it is a PID, every ideal is principal. So because D is a PID and P is irreducible, we have that the ideal generated by P is maximal. Because this ideal is maximal, by the previous corollary, we deduce that the ideal generated by P is prime. P is irreducible, therefore it's not the zero element. The ideal generated by P is prime, therefore the element P is prime. So we deduce that in a PID, every irreducible element is prime. So that means, and I'm going to record it later, that means that every PID is in fact a unique factorization domain, because we showed that every PID is Noetherian. Therefore, the existence part of being a unique factorization domain hold there. That means every element, every non-zero, non-unit element can be written as a product of irreducibles. And then by a proposition that we proved earlier, we know that such a ring is a UFD precisely when every irreducible element is prime, which is the case for a PID, as we just proved. So that means that every PID is a unique factorization domain. But before going to that proof, let's look at this result, which gives us a better idea of the connection between being irreducible and being prime. So far we showed that in a PID, being irreducible implies being prime. The converse actually holds in every integral domain. So let's go through this argument that if I tell you that D is an integral domain, then an element being prime implies that that element is irreducible. So if I tell you L is prime, I can deduce that it is irreducible. So again, in an integral domain, just knowing that something is prime implies irreducibility. The converse is far from the truth. The converse is true precisely when my ring is a UFD. This is, I mean, under the assumption that I can write down everything as a product of irreducibles, this happens precisely when my ring is a UFD. But this way, prime always implies irreducible. Let's see why this is the case. So suppose an element is prime, that immediately tells me that it is not zero and it's not a unit. So I can focus on the more interesting part of being irreducible, meaning I write it as product of two elements, and then I have to show one of them is a unit. So we need to argue, we need to say why that either A is a unit or B is a unit. This is the implication that we have to show. But when L is AB, that means L divides the product. So because L is prime, we are told that L is prime, L divides AB implies that either L divides A or L divides B. Now, there is no difference between A and B, so without lots of generality, let's assume that L actually divides A. That means what? That means I can write down A as a multiple of L, so I can find some D such that L times D is A. Now I plug in the, instead of A, I substitute L times D in this equation. And I end up getting that A, so instead of L, I'm writing AB, I'm using L equals to AB and put it inside, substitute L Substitute AB for L in this equation. Now, then what? Then I get that A, and instead of this L, I write A times B. So I end up getting that A is L A times B times D. Okay, so now because I have this equation over here, and I know that L is not 0 because L is prime. So none of the factors A and B can be 0. So A is not 0. That means I am allowed to use the cancellation law. I can cancel out A's from both sides, and then I end up getting that B times D is 1, which means B is a unit. And that's exactly what we wanted to show. Again, assuming that L is A times B, we had to show that either A is a unit or B is a unit. And because here we assumed L divides A, we deduced that B is a unit. If we knew L divides B, we could have deduced that A is a unit. So in either case, we get this implication, and therefore every prime element is irreducible. But let's go back to what I mentioned right after proving this corollary, that this corollary immediately, coupled with the fact that we proved in the previous lecture, meaning every PID does satisfy, in every PID, every non-zero, non-unit element can be written as a product of irreducibles. Combination of these two results imply that every PID is a UFD, is a unique factorization domain. This is one of the important results of this course. This is, of course, the generalization of the fundamental theorem of arithmetics, which says that every non-zero, not non plus 1, -1 integer can be written as a product of primes up to sign. Okay, so let's go through the proof of this statement. Again, we have already proved the existence part, because every ideal of the PID is principal, and therefore it is finitely generated. That immediately implies that every PID is Noetherian. And in a Noetherian ring, there is no ascending, infinite ascending chain of ideals. Based on that, we showed the existence part, meaning we showed that every non-zero, non-unit element of such a ring can be written as a product of irreducibles. Now, because existence part hold, we know that the ring is a UFD precisely when every irreducible element is prime, and that is what we showed. So altogether, we get that every PID is a UFD. Now, in this course, we had proved many rings are PIDs. For instance, we showed that every Euclidean domain is a PID. And we showed that the rings like ring of integers, ring of polynomials with coefficients inside a field, ring of Gaussian integers, ring of integers when we add the third root of unity to it. So we showed all of these rings are Euclidean domains, and therefore they are PIDs, and therefore they are UFDs. So this implication is actually rather important, that Euclidean domain implies PID, PID implies UFD. The converse of these implications are not true, but the examples are not easy. I mean, in the next lecture, we show that the ring of polynomials with coefficients inside the ring of integers is a UFD. And you have seen earlier that this is not a PID. So this shows that this implication is not true. This one is not true either. But the example is a bit tricky. Okay, so altogether now we have quite a few examples of rings that are UFD, and we have a kind of machinery of understanding when a ring is a UFD. Let's see an example when a ring is not a UFD, a natural ring, a natural integral domain. And within the process, we also learn the technique. And using this technique, we can show many of the rings of the same form are not UFDs. Okay, so what is the example that I have in mind? The example is that I join the square root of -6 to ring of integers, and I want to show that this is not a UFD. Now, how should I do it? The technique is that I'm going to find an irreducible element. I have to show that the element that I'm finding is indeed irreducible. And then I find this irreducible element in a way that it is not a prime element. So as soon as I find an irreducible element which is not prime, I can deduce that my ring, my integral domain, is not a UFD. Because either the existence part fails, or if it doesn't fail, because of the proposition that we had, a ring that satisfies the existence part is a UFD precisely when every irreducible element is prime. So if I manage to find an irreducible element which is not prime, the ring cannot be a UFD. Okay, so now in order to understand a given element is irreducible or not, the first thing that we need to check is whether this element is a unit. So this means I need to start with understanding units of this ring. Units of this type of rings can be understood using a multiplicative norm function. And here we've seen an example similar to this. The complex norm is something that can help us. So we look at the map. So we look at the map that sends z to the complex norm of z squared. What is crucial about this map is that the codomain is the ring of integers and n is multiplicative. So again, the crucial properties of this map n, the crucial properties is that first, n is multiplicative, and second, the codomain is the ring of integers. So whenever we have such a map, this can help us to understand the units. Maybe not completely, but slightly. So if I have a bit more information about the norm function, then we can more or less give a description of units based on this n. Okay, so let's see how this n can help us in this particular example. So the first thing that we are going to show is that an element z is a unit in this ring precisely when its norm is 1. And then we classify what are the elements that have norm 1, and it turns out that those are precisely plus minus 1. So this part of the argument is very dependent on this particular example. This part of the argument can be applied to any, so when we add a zero of a quadratic equation to the ring of integers, we can almost always imitate this proof and deduce this implication. But this part depends heavily on the fact that -6 is a negative number. For positive numbers, indeed, we have infinitely many units. It's related to so-called Pell's equations. Pell's equation. But let's focus on this example. So z is a unit precisely when I can multiply it by some element of this ring and end up getting 1. Now I apply the norm function to both sides of this equation. I deduce the norm of the product is norm of 1, but norm of 1 by definition is 1, and norm is multiplicative. So I get the norm of z times norm of z prime is supposed to be 1. But these are integers, and in this case, they are also non-negative. They are norm of some complex number squared, so it cannot be negative. Now, the only non-negative integer that can be multiplied by another non-negative integer and end up giving us 1 is 1. So that means norm of z should be 1. Now, if norm of z is 1, that means its z times its complex conjugate is 1. But if z is inside this ring, so is its complex conjugate. That means that if I tell you z times z bar is 1, then it is a unit, because that means I have found the inverse of this element inside the ring. So altogether, we deduced this, this part of the implication, the first part of the implication, that z is a unit precisely when its norm is 1. Now, in order to understand what kind of elements we are dealing with, I can write down the real part and the imaginary part of z. Suppose z is a plus b times the square root -6, then its norm by definition is a squared plus 6b squared. Now here is the key result that can help us understand what elements we have. If b is not 0, then the second term, this term over here, is at least 6. Because when b is an integer number and it's not 0, then its square is at least 1. So 6 times b squared is at least 6. So when I add another non-negative integer, I get at least 6. It cannot be 1. That means if I tell you a plus b times root -6 is a unit, I can deduce b should be automatically 0. Because we argued that if a plus b root -6 is a unit, then a squared plus 6b squared is 1. And this argument that I presented over here implies b cannot be 0. b is 0. I go back to this equation that we have over here, and I deduce that a squared is 1, which means a is plus minus 1. But notice that when a is plus minus 1, its norm is 1. So we get this implication over here. So the implication over here follows. So norm of an element inside this ring is 1, precisely when it is either plus or -1. Plus 1 or -1. Okay, so far we understood the units. Let's find our candidate irreducible element, which is not a prime. So that candidate element is root -6. Let's start with why this element is irreducible. So we want to show that root -6 is irreducible inside this ring. This technique that I'm going to present is a common technique. So it kind of works for square root of negative of any product of primes. So maybe -15, the same type of argument work here. Okay, let's see how it goes. So we want to show that it is irreducible. The first thing that we do, we have to check why it's not a unit. Why it is not a unit is okay. So we notice that the units are just plus minus 1. It's not plus minus 1, so it is not a unit. So that's fine. It's not 0 as well. So I focus on the main part of being irreducible, meaning I'm going to assume that it is written as product of 2 elements, and I have to show that one of them is a unit. I take the norm of both sides. So norm of this element, root -6, is the same as product of the norms of z1 and z2. Now that means 6 is product of the norms of z1 and norm of z2. Notice that norm of zi's are non-negative integers. And if one of them is a unit, I'm done. This is what I want to get to. Now I'm going to assume by the contrary assumption that neither of the zi's are units. So this is my contrary assumption, that neither of the zi's are units, which means norm of them cannot be 1. So if the zi's are not units, then their norm cannot be 1, because in the first claim we showed that an element is a unit precisely when its norm is 1. So assuming that neither of them are units, I can deduce that these norms are not 1. Now, these n's and zi's are non-negative integers. They divide 6. They are not 1. So either one of them is 2, the other one is 3, or the other way around. That means in either case, either norm of z1, one of them should be 2. So either norm of z1 is 2 or norm of z2 is 2. Next, we are going to show that there is no such element. So norm of an element inside this ring can never be 2. Okay, let's see why this is the case. So suppose that there is such an element. Suppose that a plus b root negative 6 has norm 2 for some integers a and b. That means 2 is a squared plus 6b squared. Now, by a similar argument that we just mentioned when we wanted to understand units, we saw that a squared plus 6b squared is always at least 6 when b is not 0. So if b is not 0, this equality cannot hold. I cannot have 2 equals to a squared plus 6b squared. So having this star equation implies that b should be 0, which means a squared should be 2, but that's not possible because a is an integer. Square root 2 is even not rational. So it's not possible. We get a contradiction. That shows us that altogether, you see, we showed that in order to show, we showed that we wanted to show root negative 6 is irreducible. Then we took the norm of this. We wrote it as product of two elements inside the ring. We take the norm. We assume to the contrary that neither of these factors are units. We deduce that one of them should have norm equal to 2, but then we showed that there is no such element. So this altogether implies that root negative 6 is indeed irreducible. The last thing that we'll do is to show this is not prime. So that means I'm finding an irreducible element which is not prime. From there, we deduce this ring is not a UFD. So suppose it is, okay, so I want to show that it is not prime. So this is my goal. So that means I have to provide two elements, a and b, such that root negative 6 divides a times b, but it does not divide either a nor or b. So that a and b, those elements are in fact 2 and 3. Root negative 6 times negative root negative 6 is 6. So this means root negative 6 does divide 2 times 3. Now, if it was a prime, we could deduce that it should divide either 2 or it should divide 3. Now, there are many ways of finishing this proof. So one way is, again, writing what it means to divide 2 or 3. To divide 2, it means 2 is a multiple of this number. To divide 3, it means that 3 is a multiple of this. So again, we take the norm of both sides. We get the norm of 2 is a multiple of norm of z. I mean, norm of root negative 6. And norm of 3, or norm of 3, is a multiple of norm of root negative 6. Norm of 2 is 4. Norm of root negative 6 is 6. Norm of 3 is 9. And norm of root negative 6 is 6. But these cannot be possible. You see, here, this is an integer number. This is an integer. This is an integer. So these equations imply that either 6 divides 4 or 6 divides 9, but these are not possible. 6 doesn't divide 4 and 6 doesn't divide 9. So we get a contradiction. Therefore, this element is not a prime element. This is not a prime element, but it is irreducible. So we found an irreducible element, which is not prime. From there, we deduce that this is not a UFD. Till the next lecture.